unique, there's no other. This is number of adjacent elements with the same color. Okay. So there's a 0 indexed array nums of length n. Okay. Initially, all elements are uncolored, has a value of 0. All right. So we have an array nums with n elements. Okay. And they're all initially 0. So maybe that nums array looks something like this. And they're initially all 0. Onto here. Okay, and there are how many elements here? There are n. All right. You're given a 2D integer array queries where queries of I equals index of I, color of I. So for each query, you color the index I with the color I in the array nums. All right. So if we had, for example, queries of I equal 3, 2, well, that means that I go into the queries array and I go to 0, or let's do something a little different. 1, 1, 4. How about that? So that means I go into nums. Oh my gosh. I go into nums 0, 1 and I color it 4. So I go 0, 1 and I color it 4. So this is no longer 0. It becomes 4. And it has the color 4, whatever that is, right? Okay. So basically, color, really what you're doing is you're assigning each element at an index and nums to a number. Okay. For each query, return to each query, right? So if you have n queries, you're going to have n answers. Where answer I is the number of adjacent elements with the same color after the ith query. Okay, so then the previous query affects the current query, right? Because maybe in previous queries you colored certain elements, so that could increase or decrease the number of adjacent elements that have the same color. More formally, answer I is the number of indices j such that 0 to j to n minus 1 nums j equals nums j plus 1, and nums j doesn't equal 0 after the ith query. Okay? So here's an example. So we have n equals 4 in this example problem. Let's move this up over here. All right. So let's deal with this example. So in this example, we have n equals 4. So in the beginning, so what we're gonna so we want to populate our answer array, right? So let's think about where we're gonna put that. So initially our answer is empty, right? And we want to think about what we're gonna populate our answer array to. Okay. So we have n equals 4. So let's create that nums array. So nums equals 4 zeros is what's going to be put here. Right, so we put 4 zeros in the system because that's the state of nums initially, right? There's nothing colored. And then we're going to run through this query and try to determine, how many adjacent elements are colored the same or whatever, right? So initially it's like this, right? Like it's saying, so it starts like this, and then we run through these queries. So first we do is we color 0, the color 2, right? So we color the 0th element, the color 2. Now, the answer here would be 0 because, well, I mean, intuitively, we haven't colored anything yet. I mean, we've only colored one thing, so how could 2 things be the same color, right? Because we haven't colored them. So the number of adjacent things, right, would be 0. The next thing is we color 1, 2. So we go to element 1, and we change it to 2. Now the answer is 1, right? Because now there's an adjacent pair that have the same color. All right. And then we color 3, 1. So we go to element 0, 1, 2, 3. 0, 1, 2, 3. And we color it. There's a significant delay. So we go to this element 3 and we color it 1. And that will still be the same, right? Because now they're still the same. These two over here, they're still colored the same. I colored a new one, color 1. So now the answer is 1, right? And then next we change the color of element 1 to 1. So that's interesting, right? So we can either initially color something or we can recolor it, right? And recoloring can screw things up, right? Because before we had a score of 1, but now that we're going to change ones to the color of element 1 to the color 1, right? Now we've lost some of that uniqueness, right? Because now it's 2, 1, 0, 1. Right now the elements are 2, 1, 0, 1. So there's no longer this pair. So now we have to go back to 0. Right. And then finally we color 2 to 1. So we change the color of 2, element 2, so 0, 1, 2. We change the color of element 0, 1, 2, and we change it to 1. And now the answer is 2. And how do we get that? Well, now there's this pair. That's the same for 1 pair. 2 pairs the same for 2 pairs. And you'll see, so what we'll return is this answer, 0, 1, 1, 0, 2. And the answer is, wouldn't you know, 0, 1, 1, 0, 2. Okay, so the weird thing about this, right, is, well, it seems pretty intuitive. And in the brute force solution is the most intuitive, right? What we could do, technically, is we could run a query and then look through the whole entire array to find the number of adjacent pairs that are the same, add that to answer. Run another query, run through the whole array to find the number of adjacent pairs that are the same, and add that to the answer. So that's going to take the number of queries times the length of the array, right? Because for each query, we're going to have to look through the entire array to accumulate the number of adjacent pairs that are the same. So if we have 10 to the 5 queries, and for each query, we're going to have to look at all n elements, that means we're going to have to look at n elements for all 10 to the 5 queries. There's 10 to the 5 elements at most. So that means in the worst case, we're going to have to look at 10 to the 5 queries and 10 to the 5 elements for each query. So that's 10 to the 5 times 10 to the 10. That's 10 to the 10. That's going to far exceed the time limit for a problem like this. So that's not ideal, right? So we have to think of a faster way that we can do this where we don't look at the entire list, right? We don't look at all n elements every time we solve the query because it's not gonna work, right? And maybe it's perhaps because I've, solved so many problems that there was an obvious solution, but I feel like this problem really shouldn't be that difficult to determine, maybe this isn't even worth saying because it just makes me sound like a total jackass. But, I don't think that it's really too difficult to kind of walk through and reason through, okay, how am I going to do this so that it's much quicker, right? And the way you kind of do that is, well, the information from the current query, right, is based off the previous queries. So when I recalculate all of the adjacencies, like every time I run a query, it feels like we're wasting a lot of operations because it's like, all I really need to do, right, is just think about, okay, I have information about all the previous queries, and all I need to do is look at the current query and see what that changes, right? What can the current query do to my score? So instead what we'll do here, right, is let's run through this problem again, but let's think about the current score so we don't have to look through the whole system. We'll just keep track of the current score where the score is the number of elements that are adjacent. And then when we add a new element, we'll think about how that might change the current score. All right. So let's restart this problem and let's use this notion of a score to see if we can more efficiently find the solution via that approach. Okay. So let's run through the queries again. So our score in the beginning, so let's keep a score array, which is the score after we run each query. Okay, so maybe the score array will be over here. And the score array is just your answer. So, sorry, I know how to solve this. I'm just thinking about how I'm going to articulate this properly. Let's just keep track of the score array because the score array will be your answer. So let's keep track of the score after we add each query, okay? So initially our score is 0, right? And when I add in a new element, like, for example, 0, 2, when I make this 2, well, what would it take to increase the score by 1? Well, this will increase the score if I'm adding what? Okay, so if I'm doing a query So I'm trying to think about, let me take a sip of this Diet Coke and then it'll all make sense. Okay. For this first query, I'm adding 0 and 2. It's not going to increase my score because it's the first thing I'm adding, right? That's one way of stating it. But you could also state as well, making this 2 isn't going to increase my score because the thing to the left, it doesn't exist, isn't the same, and the thing to the right isn't the same. So my score is going to be 0, right? And then when I add 1 and make it a 2, well, I'm going to say, well, I make this a 2. The thing to my left is a 2, so I'm going to add 1 to the score. And the thing to my right is a 0, so I'm going to not add an additional 1 to the score. But that means my previous score was 0, right? And now I've added something, and it made it a new adjacency, so my new score is going to be 1. Okay? And then when I make 3 a 1, I turn 3 into a 1, and then I play the same game. I turn this to a 1, and I say, okay, I made this thing a 1. The thing to the left is a 0, so it's not going to increase my score. And the thing to the right, although it doesn't exist, we'll just say, okay, the thing to the right is a 0, just for the sake of simplicity. The thing to the right is a 0, so it's not going to increase my score. So my score is the same as whatever it was before, right? And I don't need to go through the whole array. I'm just saying, when I make this new addition, it doesn't change anything. So whatever my score was before, that's what my score will be now, right? So my new score now is also 1. All right, now the next thing I do is I convert what used to be a 2 into a 1. Now, this is where you have to kind of think of another case, right? There's one case where if I add something, does it increase my score by making new adjacencies? But also, if you're changing the color of something, right? If I'm changing this color, I could add something, but I could also lose something, right? So when I add this, when I change this to 1, well, did this element that I'm changing to 1 used to add to the score? Well, it did, right? Because it used to be a 2, so I used to get a 1. I used to get 1 point in my score because this was a 2 before. So since the left is a 2 and this used to be a 2, now I'm changing it to a 1, I lose that 1. So that results in losing 1 point. And then the thing to the right is a 0, so I don't lose a point there. And then I say, okay, now that I've changed it to a 1, does it add 1 to my score? No, well, this is a 2 and now it's a 1, so it doesn't add a score. This is a 1 and this is a 0, so it doesn't add 1 to my score. So all it does is decrement to my score, right? So my score used to be 1. Now, when I change this element to a 1, it loses a point from whatever my score was before because that adjacency no longer exists because I've erased it, right? There used to be adjacency between a 2 and a 2. I converted this 2 to a 1. Now that adjacency no longer exists, okay? So now my score is back to 0. So whatever state I am at this query, the score is a 0. And then I change a 2 to a 1, right? So I change this 0 to a 1. I don't need to think about... Now, when it's a 0, I don't need to think about what the repercussions are of coloring it because it's the first time it's being colored. So since it's the first time it's being colored, it doesn't matter what it changes because since it's the first time it's colored, since it's the first time this element's being colored, it's never incremented the score, right? It's uncolored, so there's no changing color, right? We had to think about the repercussions of changing this color because this thing has already been colored. We don't need to think of the repercussions of changing this thing's color because it's never been colored before, right? So when we convert this to a 1, well, then I play this game. I say, okay, my score is 0 before, right? My score is 0 before. The score to the left is 1. The score to the right, I mean... If I get a JC on the left of 1 and I get an JC of the right of 1. So that means I add 2 to the score. So now I have 2 here, right? And you'll notice in that kind of hand-wavy process of walking through this, we'll say something a little bit more formally, right, after this. But, you know, the point is here is I didn't need to look through the whole array, right? I just keep information about the previous score and then adding a new element can only affect like myself and the 2 elements next to me, right? Those adjacencies. That's what we need to think about here when we solve this problem, okay? So with that said, let's think about more formally what this means, right? So I guess the general idea is like after X queries, okay, so let me see if I can write a kind of formal thing here and make my mathematical professors from Berkeley proud. Okay, so after X queries, you have score S of X. Okay, so after you commit X queries, right, you have score S of X, right? So you do all these queries and you figure out what your score is, right? Maybe we'll color these because we're just so cute. Right, so after X queries, you have score S of X. Okay, now you process query X plus 1. Okay, so query X plus 1 equals two things, right? There's the index that you're changing at X plus 1, and there's the color that you're changing that color to at X plus 1. All right, and that's just kind of a formal way of writing this idea here, right? So the query X plus 1 equals index X plus 1, color X plus 1. Query X plus 1, index X plus 1, color X plus 1. Okay. Now, what can that do to your score S of X, right? Well, S of X plus 1 is going to be the same as the previous S of X plus and minus a few things, right? So whatever S of X, whatever my score was before, it's going to be related to that, right? But what could change? Well, minus what? If the scores before are different, right? So minus, we'll call this the consequence of recoloring plus, so we have the previous score minus the consequence of recoloring, right? So the consequence of recoloring is the idea where there were adjacencies, and now that I've changed the color of when I lose those adjacencies. So that's the consequence of recoloring, and I get in new adjacencies. Okay. So then now I got to define what these things are, right? So the consequence of recoloring is what? Well, if I have elements like this and I'm recoloring this element, right? If this new element X, this new index X, this new element at index X plus 1, well, we're going to subtract 1 if it's been so if it's already been colored, right? So the only way there's a consequence of recoloring is if it's already been colored, right? So I can't right. If it's already been colored, so this only happens if it's already been colored. So this only occurs, there's a condition, right? The consequence of recoloring, I don't really like this idea. I'm not going to do it like that. Equals, well, it equals 0, right? If the numbers, if nums at index of X plus 1 equals 0, right? Because if index plus 1 equals 0, then there is no consequence of recoloring because I haven't recolored it yet. So since I haven't recolored, since I'm not recoloring it, this is the first time I'm coloring it, there are no adjacencies related to this index, right? Otherwise, it's plus 1, or we'll say if the color an index plus 1 equals the color at previous index and next index. Ugh. Not 2, 1. It's, I don't know how to formally write this because I'm an idiot. So we'll say 1, we basically, So 1 for each neighbor with same color. That's best I'm going to be able to do it, right? So before I recolor it, right? Let's say these two systems, it's red, and the old thing was red, right? And I'm recoloring this element to be blue. Well, the score will it's gonna be before the score will have two adjacencies, right? It'll have this adjacency and this adjacency. So since I'm recoloring this system, I'm saying, well, whatever my old color was, if the thing to the left had the same color and the thing to the right had the same color, I'm gonna lose a point from my new recoloring, right? So I'm gonna lose a point here, and that's gonna make it -1, and lose a point here and make that -1. Right, or +1, so then -2 up here. Right, that's basically what I'm saying. I'm saying, okay, before I recolor this thing, what are the consequences going to be? Well, the consequences is, well, if the old color is the same as the color on the left and the old color is the same as the color on the right, then I'm going to lose 2 points, right? If it's the same as, I'm going to lose a point if it's the same on the left, and I'm going to lose another point if it's the same on the right, right? So now when I recolor it, I'm no longer going to get that point, so I have to remove it from the score, right? So it's either going to be, the consequence of recoloring is either going to be 0, 1, or 2, right? It's going to be 0 if it's the first time I'm coloring it, so there's no consequences, or it's going to be 0 if there was no adjacencies to the left or right of this current element that I'm recoloring. It's going to be 1 if there's one adjacency that used to exist, and now that's going to be gone if I recolor, and it's going to be 2 if two adjacencies exist, so an adjacency on the left and an adjacency on the right if I recolor. Okay, now the new adjacencies, it's probably easier to understand, right? Regardless if you recolor, right, it's going to be 1 for each adjacency, left and right. Right, so this will also be either 0, 1, or 2, right? But, you know, the thing about this is, we don't need to check the whole array again, right? Because when we add a new element, it's only going to affect that element, the element to its left, and the elements to its right. The element to its right, right? So we can just keep the previous score, because the previous score will capture everything from the whole system for all the queries we've done. And then we just need to think about the 3 elements that are affected by the current query, right? The element itself, the element to the left, and the element to the right. Right, so for all of them, it's just going to be this thing. We think about what are the consequences of recoloring the new adjacencies. We add it to our score, and then we return the score. That's as best as I'm going to be able to do in explaining how this is supposed to work. Okay. Now what I'm going to do also, because I am a total whatever. I don't even know what I'm doing. Okay, so let's go ahead and get right into the problem. All right, we're getting right into the problem. I've been rambling about the problem for hours now. All right, so let's go ahead and think about this. So you could use an array to represent nums, but I'm going to use a default dict to deal with the fact that, you know, if we're at element 0, there is nothing to the left to check, and if we're at the last element in the array, there's nothing to the right to check. So it's just a little bit easier to think about this using an array. So I'll call it nums equals default dict lambda 0, because you know, every element initially is 0. And if I could spell default correctly, that would probably be good. All right. And then let's look at each query. So in each query, there's the index and the color in each query, right? And then what we say is, well, we're going to keep our score array. How do I want to do this? It's always so hard, man. Think about how you're going to do this stuff. Okay, well, I'll just do the res for the solution. The first res is 0. Then I don't want it to be off by 1. That's fine. I'll just do it like that because I'm going to do it short, and there's going to be a couple weird things I'm going to do to make this work, but that's fine. Okay, so there's kind of 3 parts to this, right? The new score, so what we're going to append to res is the new score, right? That's what the previous score was, which is res -1. All right, because we're going to keep track of score like this. So this is res. So the new score is the previous score. So we're just going to use this formula, right? The new score is the previous score. I wish I didn't move this around. Is the new score. The new score is the previous score minus the consequences and the new adjacencies, all right? So let's think about the consequences and the new adjacencies. Okay, so what's the consequences of recoloring? Well, that only happens, right, if so it's 0 if nums at index equals 0. Otherwise, it's I don't want to do it all like this. So let's think about the consequences of recoloring. The quark. Consequences of recoloring, right? Equals 0, right? But if nums at this index not equal 0, then there could be a bigger consequence, right? So we plus equal 1 if the color at the left, if nums at index minus 1 equals nums at index. So if they have the same color before, now we're changing the color. So then we're going to lose a point there. And then we could also lose a point if nums at the right equals the current thing for the same reason, right? So I'm trying to think about how I can do this. Look at that. An evil, evil way of doing this in one line. So this is the consequence of recoloring, right? So I'm saying only if, right, because otherwise this will be 0. Only if the current number is 0, not 0, then we'll determine what's the effect of recoloring, right? So only if there's not a recoloring, we'll find the effect of recoloring. All right. And then what's the new... We're going to end up coloring the system then. So then we'll say, okay, the nums at index now equals this new color. And then the new adjacencies, so the new adjacencies, right, new adjacencies equals int just this. Again, right? If this equals, now that we've recolored it, to the left, are they the same color? And to the right, are they the same color? We get 2 points that way. All right. And then what we do is we just append that to res. So now we say res at negative, our new solution res at -1 is what our old solution was, plus minus the consequences of recoloring, plus the new adjacencies. And at the end, we return res 1 forward because the first element is just a dummy element in res. All right. And with that, we cry because our solution is just so damn ugly. Yeah, it's slow. It's the runtime's fine. It's just the fact that I'm doing this on one line is creating additional operations. But in terms of the actual big O notation, is the same. So I'm not going to worry about that too much. Okay. So let's say M is the length of queries, right? And let's say that N, well, N is the length of the list. It's already listed there, right? But we'll just say that, the length of the list. All right, so for this problem, right, we have to look at, for space, well, we have to create a reference for each number so we can keep track of the color of each number in nums, right, of each element in nums. So that's going to be big O of N space. And then we just look at each query and then we color numbers accordingly. But, you know, there could be a billion queries. If there's only 4 elements, we just keep coloring those 4 elements. So we don't have to think about queries in terms of the space. In terms of time, though, it's the opposite, right? Because we have to look at each query. And then for each query, we do a constant operation to find out, you know, the consequence of recoloring. We do a constant operation to set this element in nums. We do a constant operation, and then we append res. Well, I guess then, so it's N plus M, right? Because we have to create an answer array res that has a response to each query. So we have to create M answers for M queries. So that's N plus M space. We have N space to handle the color of each element in the array. Then we have M space to populate the number of queries. And then for time, when we just look at M queries, we do 4 constant things. So that's constant time, constant operations for all M queries. So that's big O of M. And my computer's freezing. So let's whatever. All right. Peace out, guys. Hopefully that was a little bit helpful. I definitely rambled a lot today on this one.